Now what happens if the probe is not balanced properly? We'll see shortly that this distorts the waveform. So we can do a quick test to see whether our scope probe is balanced properly by just measuring a test signal. So let's do the following. Suppose that the capacitive voltage divider we call X without the value of the function generator voltage, and the resistive voltage divider, let's call that Y. So when we balance it, this was 1/10 and this was 1/10. But suppose now that this is bigger than this. Let's take this equation, let's work out some of the details here. So divide through by C sub A, so again we get this term which should be C sub B divided by C sub A, and likewise here we'll divide through by R sub B, so I get R sub A over R sub B. And so that implies that this term here are related by this inequality, but because we're taking the reciprocal, we're going to flip the sign of the inequality around. So that means that C sub A divided into C sub B is actually less than R sub A divided by R sub B. And by cross multiplying, we then get that R sub A times C sub A is greater than R sub B times C sub B. And what does that imply in terms of the actual signal that we're going to see? Suppose that the voltage that we're measuring is a step that goes from 0 to V sub P volts very, very quickly. And what's going to be the value of the displayed voltage? Well, the voltage here is equal to this voltage plus this voltage at every instant in time. And the current that flows in the capacitor is C dV dt. So I can solve for this current and for this current. Now whatever voltage is here, we can also solve for the current in the resistors by taking that voltage and dividing by the resistance. And likewise over here. Now the current I in this short circuit is no longer going to be 0 because we're going to see a very large change in current on this side but not on this side. T equals 0 plus, we have a very rapid change in voltage. In other words, a slope. And that's going to be equal to the derivative of this, which you can then write as the individual derivatives of the voltage across C sub A and C sub B. Now the voltage across these two are also equal to V sub P. These derivatives are literally infinite, and so this is much, much bigger than the value that's here. Find the current, we'll multiply by the capacitance. Even though it's small, we're multiplying by a very large derivative. Current that's flowing in here is going to be C times the derivative of this voltage, and likewise the current here. But that's huge compared to the value of V sub P, and the value of V sub P divided by these resistors is roughly the current flowing in this branch. Current that flows in these two capacitors is the same as the current that's flowing in here, but the current that's flowing in here is going to be the total capacitance times the derivative of the voltage if this current is essentially 0. Total capacitance is the series combination of C sub A and C sub B, which is the product over the sum, times the derivative of V out. Now the voltage that we see here is going to be the integral of the current that flows in here divided by the capacitance C sub B. We're going to integrate this expression. You can pull out the C sub A CB over C sub A plus C sub B, because it's not a function of time. And the C sub B's will cancel, and you're just left with C sub A over C sub A C sub B. Take the integral of dV out dt times dt. dt's cancel, we're taking the integral of just one dV out, and that's just the value of V out. That's going to be equal to this capacitive voltage divider, which we call X on the previous page, and V out at this instant in time is just equal to V sub P. For t greater than 0, we basically have a DC input. So the current in the capacitors is going to be equal to 0, and essentially all this current just goes down this path, and we get a voltage divider of 1/10. Or we just call this voltage divider of 1/10 just Y. Again, V out is just equal to V sub P. I said that X was greater than Y, so what happens here at t equals 0 plus is that we have a voltage that's larger than the voltage here when we have a flat input. What we got here is a circuit that has a spike and then an RC decay. This is called an overcompensated probe. You hook up a square wave and you see this type of a picture, and you know that your probe isn't balanced. You need to adjust the capacitance to the condition where this is without that spike, which is flat across. On the next page, we'll take a look at solving for the case where X is less than Y. Now, if we take the same condition but now make the capacitive voltage divider less than the resistive voltage divider, we still get the same result. It's just that this value here is smaller than this. This will stay the same. Now this will be the same because we got the same resistive voltage divider. So what you're going to get is a rounding on the curve now instead of a overshoot and then a kind of a RC decay. So here we got an RC charging type result. This is called an undercompensated probe, and that corresponds to our previous result but with the inequality flipped. So if you're given a square wave as an input and you have an imbalanced probe, if you have the overcompensated case, we saw that you go from 0 to X times V sub P and then eventually to Y times V sub P, which is equal to our 1/10 divider. Now, we analyze this side of the square wave, which had a positive slope. Now, if we analyze this side, we have the same results, but we have a negative slope. So we'll get the same result, just an opposite sign. So here we jump by x times v sub p, and now we're going to drop by x times v sub p, but a minus. So we take the value here, and then just subtract x times v sub p. And it's going to repeat itself. The difference between these two levels is just x times v sub p. So if you see this, you know that your probe was not properly compensated, and you just can use this waveform to essentially adjust the capacitor such that this overshoot and then eventually RC decay just goes back to a straight line. If you had the undercompensated case, begin the same argument we just did over here, kind of come up and then we charge up, and then the slope changes, so we're just going to drop by the same amount, again x times v sub p, and then we'll RC decay down to 0 volts, and then back up again and back down again. And again, the difference between this top and this part over here is just x times v sub p. But again, this is not properly balanced. I need to adjust the capacitor so that this disappears, just like over here. Just make that into a square wave. So you get a replica of your input, essentially by a factor of 1/10. In this lab, we're also going to be looking at using a potentiometer. This is a 3-terminal device that has a rotatable shaft or an adjustable set screw or a slide. And here are 3 pictures that we had in the ECE 201 ebook notes, where I've got 3 terminals, call them A, B, and C, on all of these devices. And then in our lab, we're going to be looking at another kind of potentiometer. The way this thing's made inside here is that there's a track of carbon and a resin that creates a resistance between terminals A and C. With terminal B, there's a connection with the shaft of a piece of carbon that's pressing on the track between A and C. So you're getting a percentage of the total resistance between A and C. Now with this type of potentiometer, you're just doing one rotation and going from one end to the other end. On a pot like this, there's a set screw that takes many, many turns to go from one end to the other end of the track of carbon material. A slide pot is just simply a one movement going from one value to the end value of the total pot resistance. We're going to look at a variation of this one with a set screw in lab. What's the equivalent circuit of a pot? Well, in ECE 201, we had the following. Between terminals A and C, there's a total resistance, this is the track, and then we're tapping off part of that. As an equivalent circuit, we can then write this as just a 3-terminal device where I've got a resistance, I'll call it R1 here and R2. This is going to depend on where you are rotating the shaft or the set screw or the slide switch. But your total resistance is just R1 plus R2. Now, we could write R1 as a fraction of the total resistance of the pot, where alpha is a number between 0 and 1. On the pots in the middle, we have half the value of the total potentiometer resistance. If we're a quarter of the way, then we'd have a quarter of the resistance. So we're going to model that as our formula for the potentiometer, allow us to do some calculations. We have the value of R1 expressed as a percentage of the pot. Let's solve for R2 given this equation and the fact that the pot is the total resistance. So again, our value of alpha is between 0 and 1. This indicates the position of the shaft or the set screw or the slide that we're using. Now the total potentiometer resistance we said was R1 plus R2, but we're saying that R1 is equal to alpha times our pot, a percentage of the total resistance. So then we solve for R2. So here's R2. Let's put this on the other side of the equation. Then is R pot minus alpha R pot. So you can pull out the R pot. And so I'm left with 1 minus alpha times R pot. If we're in the center position, alpha is a half, and we get R1 equal to R2. If we're a quarter of the shaft rotation, then this will be 3/4 of the total pot resistance. So we have a nice formula for calculating equations in terms of our results as a function of shaft rotation. In this lab, we're also going to be using capacitors, and like resistors, they have a color code. Now, there's a lot of letters and numbers that appear on a capacitor's body, usually stamped or painted onto it. But I'm looking for 3 numbers and a letter that's either M, K, J, G, or F. So you might have a letter after this like T, depending on the manufacturer. The way to interpret this is the following. So here's 2, here's 0, and then 10 to the 4th. But this isn't farads, but it's actually picofarads. When capacitors are sold, they're either in microfarads or picofarads, and if they're using this color code equivalent, they're referring to it in picofarads. So I've got 20 times 10 to the 4th, which is 200,000 picofarads, and that would be 200 nanofarads. If the letter K is there, then it's got a 10% tolerance. When you look at a catalog, again, you'll see things that are listed in picofarads or in microfarads. Even though this is in our engineering notation, you might see something like this, although probably more likely you'll see 0.2 microfarads, with again a 10% tolerance. So for Lab 3, which is Wheatstone bridge applications, our purpose was to look at some of the unique properties of a Wheatstone bridge in terms of cancellation. We looked at some of these properties and used it to explain how a compensated probe works. The concepts that we covered was a Wheatstone bridge using resistive and reactive components, the use of a balanced bridge to compensate for stray capacitance on a measurement cable, and the equivalent impedance of an oscilloscope being changed by the process. and lastly, capacitor coating. The laboratory techniques we're going to take a look at in this lab is using a digital multimeter to measure a capacitance. We're going to measure resistance and capacitance with a Wheatstone bridge. And lastly, we're going to learn how to do a procedure for compensating an oscilloscope probe. And this is lab number 3, Wheatstone bridge applications.